Hello, welcome you all for this new video session. In this, we will discuss steady state heat transfer in one dimensional problems. What is steady state heat transfer? Steady state means the heat transfer it doesn't depend upon the time, it is time independent. We already know what is heat transfer. Heat transfer will take place when there is a temperature gradient. It may be within the body or between the body and the surrounding. Okay, there are different modes of heat transfer: conduction, convection, and the radiations. We are discussing steady state heat transfer in one dimensional problems. Any problem can be considered as one dimensional problem, two dimensional, and three dimensional. It is depend upon the accuracy required and the rate of heat transfer in different directions. Okay, we need to analyze it. Okay, now as there are many applications, there are many engineering system which falls in this category one dimensional. We are discussing steady state heat transfer in one dimensional problem, one dimensional, one direction. In one direction means the temperature gradient it is only in one direction. Okay, in this we are deriving the differential equation or the governing equation for steady state heat transfer in one direction. In this we have taken a slab which is of thickness dx, and we are deriving the differential equation. The differential equation which tells the behavior of the problem. The objective of this derivation or this section, it is to find the temperature distribution in a given problem or given body. Here we have taken a slab which is of wall thickness dx. When the heat entering into the system and leaving the system, the heat flow it is not the same. There is some changes is there. This heat entering and heat leaving, this difference it is denoted as in the differentiate form dx dqx divided by dx into dx, where qx it is the heat flux, dx it is the thickness of this body. What is the heat entering into the system or into this wall thickness, that is qx into a, and what is the heat generated it is also called as the source, that is qa dx. Okay, this part what you can see, it is the section means it is the thickness. Okay, this thickness or this section we are considering from at a distance x from the left face. What is the heat entering into the body? It is qx into a, where qx it is the heat flux on the left face, and a is it is the area of this wall thickness, and this qa dx it is the heat generated. For equilibrium of the body, what is the heat entering and what is the heat generated in the body, that sum should be equal to heat leaving the control space or the body. The heat leaving the body it is qx. There is obviously some difference will be there. This differentiate or this change in the heat rate, it is denoted as the differentiate form dqx by dx over the length of dx. Okay, the conduction it is quantified by the Fourier's law. So we know the Fourier's law, where heat flux can be expressed as the thermal conductivity and temperature gradient. Okay, substituting this value qx in these equations, we have this. Okay, where q it is substituted as minus k into dt by dx, where qx it is substituted as minus kx dt by dx into a. What is k here? It is thermal conductivity in x direction means it is one dimensional problem, so the heat gradient transfer takes place only in this direction, dt by dx into a, and this is the heat generated in the body, q into a into dx, that is equal to Qx, again this Qx it is substituted as minus kx into dt by dx a. So minus kx dt by dx into a, then this plus dqx by dx into dx, where qx it is substituted this value, so it is d by dx minus kx into dt by dx into a dx. We have this same value in both sides, so it is cancelled here, and area into dx, when it is cancelled we have the same value here, this one it is cancelled, so it is left with this value and this value. In these two terms, a dx elemental value it is same value, so it is cancelled. So what is left, that is q is equal to minus d of dx minus d by dx k into dt by dx. Okay, taking this in this side, it is, this is the expression what is left with. This is the governing differential equation for the steady state heat transfer for one dimensional problems, where dt by dx it is the temperature gradient, and k it is the thermal conductivity, and q it is the heat generated. It is also called as the source when it is heat generated, and when heat is consumed it is called as the sink. Okay, here the solution can be solved by applying the boundary conditions. There are three types of boundary conditions. One is specified temperature. What is the temperature at the left face or right face? Okay, that is the one boundary condition. And second boundary condition, it is specified heat flux. For example, on the left side, the left face it is insulated. Okay, such type of boundary condition. And the third one, convection heat transfer. Okay, by applying or by using the boundary conditions, we are finding the temperature distribution or the temperature at any given point. Okay, this is the differential equation. For this differential equation, we are using the boundary condition to find the temperature distribution. The objective of the heat transfer in 1D heat conduction, or the steady state heat transfer in 1D heat conduction, is to find the temperature distribution in the body. Okay, thank you very much.